Here we have a little overview of how to conduct a factorial ANOVA, and there are a few things that are distinctive, so pay attention even in step 1 here. So we're going to use the problem that's outlined in your book. I've changed a little bit of the description. We're looking at testing the hypothesis that sensitivity, high versus low, and perceived performance, success versus failure, impact negative mood using alpha 0.05. So we've already described this problem, but let's take one more look at it because we want to pay attention to where these variables are. So our first factor, we'll call it, like the independent variable, is sensitivity, high versus low. And make note that this is our column factor. It's important to make note of this because we'll use those terms, columns and rows, quite a lot. So this is the column factor. When we're looking for a main effect, this is what we're comparing, low versus high sensitive people using these column means. And factor 2 is our perceived performance, success versus failure, and this is our row factor. And again, we're going to use that quite a lot, and these are the means that we'll be comparing for our rows. And right down here in the corner, we have our grand mean that we'll be using for quite a few calculations. So we'll be parsing the problem a little bit differently than we have before. First off, we're going to do just what we did, write down the factors and make sure we assign them columns and rows so that we're really clear when we do calculations. And then secondly, we'll define populations, and we have 4 of them in accordance with the number of cells. We have population 1, high sensitive people who perceive that they had a successful performance. Population 2, high sensitive people again, but those who perceive failure. Population 3 is low sensitive people who perceive that they had a successful performance. Population 4 is low sensitive people who perceive failure. And our null population are those with no differences in the dependent variable across conditions. So we actually have a number of hypotheses, and we are still in step 1, so you'll be doing those 3 things. You'll be defining the variables, defining the populations, and then writing out the hypotheses. And so we're going to have one hypothesis for each factor and for each interaction. So the research hypothesis, using our example, we would write as H1 columns, and remember, that's why we need to be really clear. You could also write the name of the variable here, but this column is used quite a lot. There will be a main effect for sensitivity. The null hypothesis, there will not be a main effect for sensitivity. And what does it mean actually? It means high and low sensitive people will differ in negative mood regardless of perceived performance. Then we'll have another hypothesis, your hypothesis for the rows. And you can just state it like this: there will be a main effect for perceived performance, or there will not be a main effect for perceived performance. And what that means is people's success or failure perceptions will impact negative mood regardless of sensitivity. So there's an independent effect of this row variable. And then finally, we have the interaction in this 2x2 ANOVA. And we would say there will be a sensitivity by perceived performance interaction, or there will not be a sensitivity by perceived performance interaction, and that might be interpreted as negative mood of high and low sensitive people will vary according to whether they perceive success or failure in their performance. And when you're writing it, if you have a significant result, this is the kind of language you'll want to be using when you write your concluding statement. Next, we describe the comparison distribution in step 2, And the distribution is still the F distribution, but degrees of freedom are calculated separately for each test. So the first number, that smaller number, DF between, well, for factor 1, for the first main effect, the columns, we have sensitivity, low versus high, and the degrees of freedom are the number of columns minus 1. So in this example, just 1. And you can see, of course, the columns, just 2 columns under the sensitivity variable. In factor 2 are rows, perceived performance, success versus failure. Well, here we can see 2 rows. And so number of rows minus 1, 2 minus 1 equals 1. Our interaction is a little bit longer, sensitivity by performance. We start with the number of cells. And by this, when we talk about cells, we're just talking about these in the middle, related to those 4 populations we described. These on the outside are called the marginal means, and they're not included when we count our cells. So we have the number of cells minus the degrees of freedom columns, minus degrees of freedom rows, minus 1. And in this case, we have 4 cells, minus 1 DF column, minus 1 DF rows, minus 1. And so we end up with 1 degree of freedom in this problem. The second number for our ANOVA is DF within, and it's just, you can calculate it a couple of ways. Either the total N, this big N meaning all of the individuals, minus the number of cells, so minus 4 cells, or the sum of DF1, DF2, DF3, all of those calculated separately. When you're running your calculations, you'll get the same number either way. Next, we look up cutoff points. And so as we already saw in our 2x2 ANOVA, F alpha is the same for all the tests. DF within will be the second number, or the denominator number in the ratio. And the top number, or the first number when we're entering it to look up the cutoff point, well, in our example, it was 1 in every case. So we're going to have 1 F alpha for each of these 3 tests. But this isn't always the case. In a 2x3 ANOVA, it would differ. 2 columns, well, DF columns is 2 minus 1 equals 1. But if we have 3 rows, then we're going to have 2 degrees of freedom for the ANOVA test when we're comparing the rows. And we have 6 interactions, and so we would have DF calculated as 6 minus 1, representing the DF columns, minus 2 representing the DF rows, minus that extra 1 for degrees of freedom equals 2. And of course, DF within depends on the number of individuals for each cell. In our example on the left, we had 5 individuals per cell, and so that brought us to 20 minus 4 equals 16. We haven't defined that in the right-hand example, so we can't calculate that. And step 4 and 5, we calculate F ratios, decide and conclude. And the F ratio, it's a pretty long process, guys, but we'll do a couple of problems with it. And then we'll move into a more robust tool. But we're going to do a couple of these, so you just kind of get the feel for it. We'll work out calculations in the spreadsheet, and you'll also be asked to create a graph. And then deciding and concluding. Your decision is easy. For each test, if F observed is greater than F alpha, you reject HO. Remember, the F distribution is always, it's a skewed distribution, so we're always doing a one-tailed high test. And your conclusion is probably going to be several statements long because you have to describe the main effects, including the means and F ratios like we did in the one-way ANOVA, and also the interaction effects. And that language that I used in that third column on slide 5, that's the kind of language you'll be using to write your concluding statement. So on we go to the actual solving of the problem.